Mastering data structures. Essential concepts for algorithm enthusiasts. Data structures are the building blocks of efficient algorithms, enabling programmers to store, organize, and manipulate data in ways that optimize performance. Whether you're preparing for technical interviews or aiming to deepen your understanding of computer science fundamentals, mastering data structures is crucial. In today's fast-paced tech landscape, proficiency in data structures can be the difference between an average developer and a standout problem solver. This guide delves into key data structure types, their applications, and how they impact algorithm design and efficiency. The foundation of efficient algorithms. Data structures provide structured formats for storing and accessing data efficiently. They influence everything from search operations to memory management in modern computing systems. Choosing the right data structure often determines whether an algorithm runs in linear time versus exponential time. For instance, using a hash table instead of a list can drastically reduce lookup times in many scenarios. A solid grasp of data structures allows developers to write code that scales well with increasing input sizes. As datasets grow larger, inefficient choices lead to significant performance degradation. Common data structures include arrays, linked lists, stacks, queues, trees, graphs, and hash tables. Each has its own strengths and weaknesses depending on use cases and requirements. Arrays provide constant time access but fixed size limitations. Linked lists allow dynamic resizing at the cost of slower random access speeds. Stacks and queues, specialized structures following LIFO and FIFO principles respectively. Trees and graphs represent hierarchical or networked relationships effectively. Hash tables enable quick lookups through hashing mechanisms. Understanding time complexity and space efficiency. Time complexity measures how long an algorithm takes relative to input size, while space complexity refers to memory usage during execution. Optimizing both aspects is critical when designing solutions for real-world problems where resources might be constrained. A good balance ensures practical applicability across different hardware environments. For example, bubble sort has O(n) superscript 2 time complexity, making it unsuitable for large datasets compared to merge sort, which operates in O(n) log n. Analyze trade-offs carefully. Sometimes reducing time complexity may increase required memory consumption or vice versa. Evaluating common operations. Finding optimal solutions requires evaluating common operations like insertion, deletion, traversal, searching, etc., against each data structure type. Insertion into an array typically involves shifting elements, leading to O(n) time complexity, whereas inserting into a linked list occurs in O(1) if we have reference to node position. Searching within unsorted arrays results in linear scan operations taking O(n), while binary search on sorted arrays reduces this significantly down to O log n. When working with tree structures, depth-first search traversals offer distinct advantages over breadth-first approaches based on application needs. Diving deeper into core data structures, let's explore some fundamental yet powerful data structures used extensively in software development projects worldwide. Arrays form one of the most basic constructs, allowing contiguous storage of homogeneous elements accessible via index positions. However, arrays suffer from inflexibility regarding capacity changes once initialized, since they occupy predetermined block of memory. This limitation leads practitioners towards alternatives such as dynamic arrays, which automatically resize themselves upon reaching capacity thresholds. Dynamic arrays maintain similar access characteristics while providing flexibility through amortized constant-time insertions at end positions under certain conditions. Exploring linked list variants. Unlike arrays, linked lists consist of nodes containing data along with pointers. Referencing next/previous nodes, forming chains rather than blocks. Singly linked lists only support forward navigation, while doubly linked lists enable bidirectional movement, facilitating easier deletions and modifications. Circular linked lists create loops by connecting last node back to first element, offering interesting properties useful in various implementations. Each variant comes with its own set of benefits tailored specifically toward particular problem domains requiring specialized handling techniques. Singly linked lists, simplest implementation but limited functionality due to lack of backward references. Doubly linked lists, more versatile, supporting complex manipulations though consuming extra memory for additional pointer fields. Circular linked lists, useful in scenarios involving rotation or maintaining perpetual cycles without explicit termination points. Stacks and queues, fundamental linear structures. These simple yet effective structures follow strict ordering rules governing addition/removal sequences, ensuring predictable behavior patterns. Stacks implement last in first out, LIFO, principle, meaning recently added items get processed before earlier ones, ideal for recursion or expression evaluation tasks. Queues operate under first in first out FIFO model, preserving original orderings among queued entries suitable for task scheduling situations. Both structures find numerous applications ranging from browser history tracking to printer job sequencing, illustrating their versatility across diverse contexts. Tree structures, hierarchical organization models. Trees represent parent-child relationships visually resembling inverted pyramids, providing intuitive representation methods for hierarchical data organization. Binary trees restrict each node having maximum 2 children, simplifying analysis, although limiting potential branching possibilities inherently. Binary search trees enhance standard binary tree functionality by imposing value constraints, ensuring ordered arrangements, aiding faster searches. Other specialized forms include AVL trees designed for self-balancing purposes, preventing degenerate scenarios resulting from skewed distributions. Binary tree, basic form permitting up to 2 descendants per node without enforcing order relations. Binary search tree, BST, maintains ascending/descending sequence, facilitating efficient retrieval operations. AVL tree, automatically adjusts height differences, maintaining logarithmic time complexities even after frequent updates. Red-black tree, another balanced BST variation employing color coding strategy for structural consistency maintenance. Graph theory applications in modern computing. Graphs model connections between entities, abstractly capturing interdependencies present within networks comprising vertices/nodes interconnected via edges representing associations. Directed graphs allow asymmetric links, while undirected versions feature mutual connectivity, implying bidirectional pathways exist between connected pairs. Weighted graphs assign numerical values to edges, quantifying relationship intensities, applicable in routing optimization challenges faced daily by logistics companies globally. Applications span social media analytics, recommendation engines, traffic flow simulations, showcasing relevance extending far beyond academic confines alone. Undirected graph, symmetrical edge connections indicating reciprocal relationships existing independently of directionality considerations. Directed graph, asymmetric nature reflecting directional dependencies commonly seen in web page linking structures. Weighted graph, incorporates quantitative measures assessing strength magnitude associated with pairwise interactions. Acyclic graph, contains no cycles, ensuring finite paths prevent infinite looping scenarios during traversal processes. Hash tables, optimizing lookup performance. Hash tables utilize cryptographic functions mapping keys uniquely onto bucket indices, minimizing collision probabilities, enhancing overall speed metrics considerably. Collision resolution strategies like chaining and open addressing determine effectiveness levels experienced throughout varying workloads, exhibiting differing frequency distributions. Proper sizing plays pivotal role influencing performance outcomes, since oversized tables waste resources unnecessarily while undersized ones trigger excessive rehashing events, degrading system responsiveness. Selecting appropriate load factors helps strike equilibrium, balancing storage utilization rates against computational overhead incurred during probing phases. Advanced topics and practical considerations. Real-world implementations require considering nuances affecting actual performance, including cache locality effects impacting CPU pipeline efficiencies indirectly. Memory fragmentation issues arise frequently, especially when allocating/deallocating objects dynamically, necessitating careful planning ahead of time regarding expected usage patterns. Garbage collection behaviors vary widely across languages, influencing choice decisions made concerning object lifetimes management practices adopted universally nowadays. Parallel processing demands introduce new dimensions requiring synchronization primitives, preventing race condition occurrences amidst concurrent accesses happening simultaneously. Designing effective solutions using appropriate tools. Proficient engineers must recognize situational context, determining best fit selections, avoiding rigid adherence solely based on theoretical preferences detached from operational realities. Evaluate requirements, thoroughly identifying primary operations guiding final selection process, ensuring alignment between intended functionalities and chosen architectures. Consideration extends beyond mere existence criteria, encompassing scalability expectations shaping future expansion capabilities essential for sustainable growth trajectories. Performance benchmarks serve as vital indicators measuring success against predefined goals, confirming viability status before deployment stages commence. Conclusion: mastery of data structures empowers developers to craft high-performance solutions capable of tackling increasingly complex computational challenges facing industry professionals nowadays. Continuous learning remains imperative given rapidly evolving technologies demanding updated knowledge sets aligned closely with contemporary standards prevailing currently active within competitive market spaces.